how does adaptive controller, true adaptive controller works? There are many adaptive control labeled activities in industry. Hardly any of them is adaptive control. They misuse the term. Adaptive control means as follows. This is the block diagram of entire adaptive controller. This is the machining process. Input to the machining process is the feed. Output is the force. This could be torque or power as well. Okay, and this is the machine itself. This is the trajectory generation controller, and so on. This is the feed drive system itself, and this is the machine tool. For us, all of the drives are buried inside this box. If it is 3-axis, 5-axis, we don't care. Input is feed command from the NC programmer. Output is the real feed that the machine travels along the toolpath. Okay. This one represents the machine. Okay. But you don't know what the machine is because you are not the builder of the machine tool. For this particular application, we really don't need to know. The second part is the cutting process. You don't also know the cutting process. Why? You don't know the part geometry from outside. And there are holes, cavities, and if you are machining die, engagement conditions are continuously changing. We have no idea. So we don't know this one either. So I assume that cutting process is a first order system, and this is a first order system, although it has higher order, because we are not controlling the process at 1 millisecond intervals. You can't anyway. PLC will not allow you to do that. So typically, we are controlling the machining process at 100 millisecond or 200 millisecond intervals. If you keep changing the feed rate violently in short time intervals, you will ruin the part. Okay? So adaptive controller must work at a very low frequency, half a second, like that. And therefore, approximating the whole complex system, cutting as well as whole drives of the machine tool together, can be approximated as a second order system like this. In fact, if you make it, if the machine is a bit fast, you can even assume the whole thing is almost like a first order system. It will simplify the algorithm a lot more. But if this is the transfer function of the system, we don't know B0, B1, A1, and A2. These represents the machine dynamics plus the hardness of the material, depth of cut, width of cut, engagement conditions, everything. These parameters are dependent on everything. We don't know them. But we know input command, and we need to measure force, power, or torque, one of them, because that's what we want to control. From these two inputs, we can estimate B0, B1, A1, and A2 in real time using recursive least-square identification technique. It is a well-known technique in the literature, and then you can design the controller. This one has a pole placement controller. T is just a gain, one number. R and S, these are polynomials. This has two parameters. This has also two parameters, 4 parameters, and these two polynomials are calculated from B0, B1, and A1 and A2 at every control interval. Then this is the input force. Let's say the maximum load the cutting tool can handle is, let's say, 1000 Newton. You set 1000 Newton here, and the controller will automatically manipulate the feed rate to make sure that output force is also maintained at 1000 Newton. That's the adaptive control. You can put power or torque. Power is useless because it very much depends on the spindle. Or you can put torque. Torque is proportional to radius of the cutter and angle, the force acting on the tool. So can we estimate cutting torque by measuring the power from the spindle drive? It's not that easy. Okay, it's not that easy. Very, very much noisy, and also we have friction in the bearings, spindle bearings. Okay, we have to separate friction first. And these are the results. These are step changes, and you see these spikes. These spikes, you have to slow down the machine fast. Otherwise, these spikes will break the tool anyway. But this is severe test. These are step response tests. Okay. Okay. Then this is how the feed rate is manipulated by the controller. These are the identified parameters in real time, as you see how they are changing. But the force is kept exactly at 1,200 meters, as you see. You can also put a varying force here, doesn't matter. Then it will track that force. Let's say you have a turbine blade, and you know the stiffness of the blade along the tool path. You want to limit the deflection, let's say at within 50 micron, and you know the stiffness. Then you know the force limit at each point. You can schedule that, and you can do that too. We implemented this in 5-axis flank milling of impellers. Okay, that's adaptive control.